Okay, so I saw this problem a couple of weeks ago presented as a kind of algorithm interview question in Go. It's the LRU cache, and I think it's quite interesting for a couple of reasons. First of all, it's probably one of the most interesting algorithms for combining different data structures in order to get all of the benefits of each. And it's especially interesting because, at least in my implementation, it makes use of the linked list, and the linked list is fairly rarely used in most modern programming languages, and fairly rarely in Go. So I thought it was interesting for those two reasons. So I'll explain the LRU cache quickly. The LRU cache is a least recently used cache. So it operates mostly like a normal cache, which is that you set a value and then you can retrieve that value by its key later. So it has a set and a get method like, you know, almost every other cache. But the least recently used part means that the cache has a capacity, a maximum number of elements that it can contain inside the cache. And if you exceed that capacity, then the least recently used element is removed from the cache. So if you set 3 or set some items and get some items, when you set an item and you go over the capacity, the last recently accessed element is removed so that you maintain your capacity. And that's pretty much the LRU cache, but it's quite an interesting one. So I thought we'd have a go, or at least I'll have a go at implementing it today. Now, let's talk quickly about how I would think about this problem. Now, there are two main requirements, right? The first is that of a normal cache, and I'll write these up here. The first is that I set an element, then I can get the element, okay? So if I set something in any normal cache, I set it, I can retrieve it. Very simple. But the second requirement is that, you know, we have max capacity and we maintain the most recently used elements, okay? And remove least recently used, okay? Now, this first set and get, i.e. being able to dynamically set a value and then retrieve it by its key, should be screaming at you, map. We're gonna use a map to set and then retrieve this. Okay, and the benefit of the map is that no matter how many elements we have, no matter how large this cache gets, with a map we can retrieve in constant time our value. Okay, so it scales in constant time regardless of the size of the cache. But so we want to maintain, if possible, that performance, the scaling ability or capability when it comes to the LRU cache. So with the LRU cache, what we need to keep track of, we need to track least recently used, okay? So we need to map some kind of order so that we know this was the most recently used, this was the least recently used, and everything in between. And obviously when you're thinking about order, an array would jump to mind, right? And an array is a standard way we think about using a list. The array means that we can sort in order everything from most recently used to least recently used, pop off the least recently used when we add a new element at the front, okay? We maintain that order of recency. But my view at least is that an array is not the way to go. And the reason I've tried to do a quick drawing here to display why it's not the best way to go. If you think about this as an array, we have these 4 elements in order. What we're going to be doing when we're making this LRU cache is reordering items. So if an item is already in this array and then we use it, we need to move it to the front. Now the way that you'd have to do that in Go is you'd have to take this element, say element index 2. You're going to have to, in order to achieve this in Go, you're going to have to copy these, or rather, you're going to have to copy this, move this to the front, and then move this forward. Now that doesn't seem like a lot of work when it's only one element, but imagine that there were, you know, I don't know, even just a few more. If I want to move this element to the front, okay, in memory. I can move this in memory, but now I have to move every single one of these elements in memory so that they maintain contiguous memory, okay? So every time I move an element in an array, I have to adjust everything that's behind it. So, my belief is instead that we should use a linked list. And a linked list, let's spread these out a little bit. A linked list, if you're represented by the nodes by these red balls here, if you think about a linked list as linked in order like this, now, because a linked list, the benefit being, of a linked list, the nodes aren't in contiguous memory. If I wanted to move this element to the front, I don't have to move anything in memory at all. All I need to do is move this pointer so that it points to this node. Let's move this out, sorry. All I have to do, if I stretch this round, is move this node so that it now points around here, delete this, and move the pointer to point to the front here. And again, let me make this more clear. And that's it. Now what we've done, without having to actually move any of these nodes in memory, have to do any of that work, we've simply changed two memory addresses, like physically enter memory addresses, and in that way, we've rearranged the order, we've moved an element to the front. And it's as simple as that. So this is why I believe that a linked list is the way to go. So if we go back to our spec here, we're going to actually use a linked list for this, okay? So what we're going to do is we're going to have a map, which is going to be able to retrieve by key. So this will retrieve by key. If I could spell retrieve, I'll just get by key, because I can't spell retrieve right now. The map is going to get by key in constant time. The linked list is going to allow us to maintain, pardon me, order, so that we maintain order, in constant time. Because, as we'll see in a moment, what we'll be able to do is, just as we've seen, when we need to move an item, we can simply take that item, change its pointer to move it to the front in constant time, as long as we know where to find the linked list element, which we'll see we'll be able to do shortly. But what I thought we'd start with, if that explanation is clear, what I thought we'd start with is simply implement a test for the LRU cache. For the first part of the cache, which is the getter and setter. That should get us going, and then after that we'll come back and think more about the LRU part of this. So the first thing we're going to do is define our interface. And as with pretty much every cache you'll ever see, you have a getter, which will take a key and return a value. This is going to be a string-only cache for simplicity. Once we have generics in Go, of course, we can make this a generic cache, but check out my video on Go generics, actually. Very exciting. Looking forward to it. I think it will make Go into the perfect language, but more on that in that video. We'll also have a setter, which will take a key and a value and set them, okay? That's our interface, which we're going to implement. And our LRU cache will implement cache, okay? And so all it needs is a get, let's just copy that for ease. And I can't spell cache, and probably this will just return as dummy string for now. Okay, so let's implement the interface. Let's start some tests just to make sure that we can hold ourselves to this. Sorry, I'll make this larger. So we just want to test that it implements the standard cache kind of feature, which is getting and setting. Okay, so all I want to do is let's make a function actually to create this cache. So LRU will return an LRU cache, and this just returns an LRU cache. Okay, so all we want is for, at the moment, is for our cache to receive a value, store it, and be able to retrieve it. Okay, so let's get our cache as a new LRU, and we'll call cache.set, and let's go for capital cities. Okay, so we're in London today, so we'll start with London. I'm going to do it all lowercase just for ease. So basically, I should be able to set UK is capital London, then retrieve it by calling get UK. We'll say if U is not London, t.fatal expected. Let me see. Expected London got whatever U is. Okay. So that's our standard test. We know we haven't implemented this yet, but this is going to test basically that the cache works in the standard way a cache does. Okay. We know it's not going to work, but we know how it's going to work, which is that we're going to use a map, right? Just as we discussed when we talked about our spec before, we're going to use a map. We're just going to set and retrieve our values in constant time. Okay, you can't do better than that. So that means we need to initialize a map here. When we're performing the set, we simply say l.m, and we set our key equals our value. Okay, that's our setter, and here to get, we return the key of the map. And if we run this, we can see down here that it's passed. Okay, so we've already implemented the basic cache. It's very simple, it's just a map. But now we need to start to think about the LRU part. And as we mentioned, for the LRU, that means we're going to have to remove the oldest element, the least recently used element, not the oldest. The last ones have been, sorry, the oldest one, the least recently ones have been get or set. We're going to remove that one when we reach capacity. So the first thing I'd like to do is actually to make this capacity a parameter. That way we can easily test it. Capacity is cap. That way we can easily test it by passing a cap, but also it makes it more flexible for different use cases if someone were going to use our library, which they definitely won't. But let's write now some tests for the LRU. Testing.t here. And just write some tests for the behavior we want to see so that we can then test that we've achieved everything, okay? So the first thing we want to do is LRU, and this time we're going to have a cap of 3, okay? So we're going to allow 3 in there at any one time. And we're going to call cache set UK London. We're going to set Germany is Berlin, and we're going to set France. Put this above because in my mind I have a plan. France and Paris, okay? So at this point, cache is full, okay? Order is Germany, Germany, France, UK. The UK is the least recently used. The UK will be popped if something else is added. So for example, cache.set, let's say Belgium, Brussels, this should remove the UK now, okay? So now we can write our first test of this, and we can say, let's say u equals cache.get UK, the test is, well, UK should no longer be present, okay? Because it should have been popped when we exceeded our our capacity here. Capacity 3, we've got, this is the 4th one, it should pop out the 3rd, okay? But next, so now let's say order is now Belgium, Germany, France, okay? And the France is now the least recently used. But remember that let me see, so the get should also update the most recently used. So if we read cache.get France, you know, and we should test not equal Paris, t.fatal.f, expected. It's so long writing these tests, and you should definitely parameterize this, but I can't bother right now. But got whatever we got. Now, the point is that doing this get here is now going to change the order. So the order now is going to be France, Belgium, Germany. Because France is now the most recently used because we got it. So France has gone from the back of the queue to the front. So next time we perform a set, Germany's going to be removed rather than France before, okay? So let's do, to prove this, cache.set, what should we do? Netherlands, Amsterdam. So this should remove Germany, okay? And now we can test it all. So we can say, let's see. So the order now should be Netherlands, Belgium, Netherlands, France, Belgium, okay? Netherlands. Okay, and now we can test them all. So we can do, let's write some test cases here. Test case, final cases. We just want to check that everything else is left. So we want to make sure that all these 3 are still here. Oh no, let's not bother prioritizing them, just do them. I'm not that lazy. So we should have n is cache.get Netherlands if n is not equals Amsterdam. Then it fails. Should be Amsterdam got whatever this is. So next we want to test that we have, what's left in this? France. Well, actually, you know, we should also test, before even this, that Germany has gone. So let's say Germany, G is not equal. So Germany should be empty. Let's see. Germany should be removed. Yeah, so that Germany should have been popped when we set Netherlands here. So we've got Netherlands, France. So France is obviously Paris, and then finally Belgium at the end. So Belgium, B, and this should be Brussels. B, and it should be P. So that's the full test of the LRU cache, okay? We're setting some stuff and we're making sure that the right things have remained and the right things have been removed. But we know for a while that this is not implemented yet. So next we need to start implementing it. So in editing I realized this video was running a bit long. So I thought we'd split the video in half about here. What we've done is we've just finished implementing the requirements for the LRU cache in tests. So we'll pick it up next time by actually implementing a constant time cache, an LRU cache in Go, which will scale with no performance degradation, no matter how large the cache gets. So we'll leave it there. Make sure you subscribe so you don't miss part 2. and leave any comments down below, and I'll make sure to address those at the end of the next video. So thank you very much for watching. I'm Sam, and I'll see you soon.